What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencastr. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencastr is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencastr's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code breakingmath, and you'll get 30% off your first month in any Zencastr paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
Spheres and circles are simple objects. They are objects that are uniformly curved throughout in some way or another. They can also be defined as objects which have a boundary that is uniformly distant from some point, using some definition of distance. Circles and spheres were integral to the study of mathematics, at least from the days of Euclid, being the objects generated by tracing the ends of idealized compasses. However, these objects have many wonderful and often surprising mathematical properties. To this point, a circle's circumference divided by its diameter is a mathematical constant pi, which has been a topic of fascination for mathematicians as long as circles have been considered. So what can we learn from analyzing the properties of circles? What shapes can a sphere take? And what can we learn from a woolly sphere? All this and more on this episode of Breaking Math. Episode 52, Round. I'm Sophia, and this is Breaking Math. With me, I have on Meryl Flaherty from episode 51. Meryl, thank you for coming on.
Thank you for having me.
And first, we have some plugs. We have a tier on Patreon of $22.46, which is pi to the E dollars. And that's patreon.com/breakingmath. That'll be a monthly donation to get a poster that has tensors on it, a definition of tensors, some introduction to how tensors are used in the general theory of relativity. If you don't want to donate every month, and if you donate $1 or more a month, you get our episodes without ads. We also have a tier where we deliver outlines, and this is the same tier, $1 or more, and that's patreon.com/breakingmath. If you want the poster, but you don't want to donate every month, we have a poster store at facebook.com/breakingmathpodcast. Just click on shop. It is $15.15 for tensor poster, which I believe is E to the E dollars, with $4.50 shipping and handling, which is $19.65 total. It's a pretty fun poster. I know that holidays are coming up. Also, you can find updates about the show on Facebook. At Twitter, we're on at Breaking Math Pod. We're starting to tweet there a little more. And we have a website, breakingmathpodcast.app. That is breakingmathpodcast.app, where we have different demonstrations such as what a Fourier series is, how to do a Sierpinski triangle by picking random points. Also, we have the game of life on the Klein bottle. So that's pretty cool. You can also check out sister podcast, Turing Rabbit Holes, wherever you find podcasts.
Also, you're telling me that e to the e is not 27?
E to the E is not 27.
But
Why is E3?
E equals pi equals 3, right? As an engineer.
We don't have engineers on this show.
Damn.
All right, so Meryl, what do you think is cool about spheres and circles and all that?
From a topological standpoint, spheres are pretty much the simplest shape you can think of. It's like join anything to a sphere, and it's still the same shape. Like take a torus, join a sphere to it, just glue a sphere. It's the same thing. It's kind of like the identity of, topological objects.
And can you explain what you mean by joining a sphere by a torus?
So suppose you had just a torus, like a regular old donut, and it's like, say you cut a hole out of that, and you cut a hole out of a sphere, and you glued those two together, well, the sphere would just kind of disappear into that torus. It would just still be the same donut. It would still have the same donut hole.
So topologically, they're interesting. I think they're interesting for other reasons. I mean, I like the fact that they could be extended to any dimension, even though they're continuous objects. I mean, you could do that with like hyperparabolas and paraboloids and all that stuff. But we're doing an episode on spheres just because they're cool. They're the simplest object, but we have all this math related to them. I mean, Euclid, as we're going to see, defined his entire system of math using spheres and straight edges. And so without further ado, here we go. All right, so first on the history of spheres and circles, which is a very difficult thing to do because planets are spherical. I mean, spheres just exist naturally. But I guess we could talk about like the early history. The early history, I mean, people didn't understand spheres very well. They understood it a lot of times through the study of pi. Until about 1000 BC, people thought pi was between 3 and 3.125, which is not very accurate. Finally, Euclid started using spheres and circles to do different proofs. And he did this with compass and straight edge geometry. And Meryl, do you want to say anything about compass and straight edge geometry? Do you want to explain maybe the limits of what you can do with it?
I mean, it's all proofs by construction. I mean, it's just like you can draw up circles and you can draw up spheres and you can like get things such as length and circumference through them, and you can, do division to find out. It's like what ratios are, and that's how we get things like pi.
What's interesting, though, is that using a compass and a straight edge, you can't do a lot of elementary things, like you can't make a sphere of twice the volume of another sphere, or you can't divide an angle by 3 or even 5. There's a very limited amount of stuff that you can do with it. However, for about 1,000 years, it was like the golden standard for math and geometry was Euclid's Elements, which we've talked about many, many times on the show. The proof that he had for the area of a circle being half the area of a rectangle is that he divided the circle into a bunch of slices of pi, basically, and made the slices of pi infinitely thin, and noted that those are triangles about the size of the radius tall with the total base length of the circumference of the circle, right? With Euclid basically proved that a circle has the area of a triangle with a base of the circumference and a height of r. So you can imagine this as, let's say you take an orange, right?
Right.
And you peel apart the orange and you lay all its slices down so that all the points of the slices are facing up, and you have the orange skin. Like if you did that in the orange and an infinite number of segments, you could make those segments simple triangles, right?
Yeah.
And then they together would all have the area of the circle.
Okay. So pretty much you're taking a bunch of triangles and adding them up to the area of the circle is what you're saying.
Yeah. And so the bases of all those triangles all put together is equal to the circumference of the circle. And the height of all those triangles, because they're all segments of the circle, is r.
So the radius.
Yeah, the radius. And so 1/2 times the circumference, which is 2 pi r, times r, leads us to the very familiar formula pi r squared, or 1/2 tau r squared.
Right, because, those of us who follow by heart will, refuse to accept pi, and tau, which is just 2 pi, is the real circle constant.
All right, and then we go on to Archimedes, who proved that the volume of a sphere is 2/3 the volume of the enclosing cylinder. And we might do this on a problem episode or something, but simply put, he did this by taking a cylinder that encloses a hemisphere, right? And then a cone that starts at the top of the cylinder and goes down to the bottom. And they noted that with every slice, the slice of the cylinder minus the slice of the cone was equal to the slice of the sphere. So since the volume of a cone is 1/3 the volume of a cylinder, it's 1 minus 1/3 equals 2/3. Again, we might do this on a problem episode. All right, so now we're going to talk about multidimensional spheres. So Meryl, how can somebody extend the definition of a sphere to more than two or three dimensions?
So the way that we usually define a sphere is in terms of metric spaces. And so what you have is you have a center point of your sphere, and you have a set of points that are all the equal distance from that point.
And what is a metric?
So metric is usually some sort of measure of distance, and I think the easiest one to go with in this case is the Euclidean metric, because that's what we use
in space and time,
yeah,
in like local space.
It's like when we're trying to say how far something is from another thing, we usually use Euclidean metric. So, the square root of x squared plus y squared plus z squared, and however many dimensions we have. So the square root of the sum of squares is the Euclidean metric.
Yeah, so and the Euclidean metric you can extend to any number of dimensions. So like if it's 4 dimensions, you take and you have like some x, y, z, and w. You just take the difference in x squared plus the difference of y squared, z squared, and w squared. Add them all together and take the square root, and you get the distance.
So, and we're talking about like something simple, like the one sphere.
And the one sphere is a circle, correct?
Right.
And why do we call that a one sphere and not a two sphere if it's a two-dimensional object?
Because even though it exists in two-dimensional space, there's only one dimension about which you can move about the curve that is the one sphere.
Which is like the angle, which is what we normally call it, right?
Right.
Yeah, so like an angle is anywhere, like in our common system, is 0 to 360 degrees or 0 to 2 pi or whatever. And that's only one dimension because there's only one number specified. However, it's embedded, right, in two-dimensional space?
Right. And pretty much what that means is that, so there's 2 dimensions that we're moving about, x and y, but we're restricting ourselves to, say, square root of x squared plus y squared is equal to 1. That's our unit circle or our unit 1 sphere.
And unit just means 1, right?
Right. Unit means that our distance from the center is just 1.
Yeah, so 1 meter, 1 foot, 1 barleycorn, whatever. So basically we have this notion of distance now for any number of dimensions. So a sphere is basically the locus of points, meaning the collection of points that are equidistant from some point, right?
Right.
And so in like 10 dimensions, right? A 9 sphere would exist in 10 dimensions, and it would be everything that was equidistant from some point in this 10-dimensional space.
Exactly.
All right, so let's say we have an n sphere, and n ball, right? If the n ball has dimension 2, then it's like a circle, right? And it's pi r squared.
Right, and actually, I'm not sure we actually define what a ball is.
A ball is, whereas the sphere is the points that are equidistant from some center, right?
Right.
I mean, a ball is everything less than that.
Right.
Well.
So the ball is everything contained in and including that sphere.
Yeah, so a 3 ball is like if I filled a basketball up with clay.
And also keep in mind, so the 3 ball would be all of the contents within the 2 sphere, because the 3 ball and the 2 sphere both exist within 3-dimensional space, but the 3 ball is actually filling up 3-dimensional space inside of that sphere.
You want to know what's interesting is that the n ball with the maximal amount of hypervolume is a 5-dimensional n ball, which is 5.264 times r to the 5th. Versus like if it's a sphere, it's 4/3, which is 4.188. And the surface area, just for trivia, of a unit sphere is maximized at 7, which is 16 pi cubed over 15, which is 16 pi cubed over 15. The n ball was 8 pi squared over 15, but n pi cubed over 15 is 33.07 versus in three-dimensional space is 12.56. And I don't know, I just kind of find that interesting. And we might do a problem episode on the relationship between the volume of balls and spheres. But Meryl, what is the volume of a zero-dimensional sphere?
Be 0.
Actually, it turns out it's 1. I guess you just count the sphere. I mean, just count the ball. All zero balls have volume 1.
Right, because my thought is a zero sphere is just a set of 2 points, right? Just like, say that it's like...
Oh, yeah, sorry, I meant a zero ball. Yeah, a zero ball has volume 1.
Okay.
Although, yeah, I guess a zero sphere would have surface area too.
Well, except, so if you're talking about a zero sphere, then that's just a set of 2 points. That's just like, say it's radius 1, then you have 1 and -1, and those are the 2 points you have in that zero sphere.
Yeah. But we also have to measure in zero-dimensional space, which I'm pretty sure is just counting, kind of.
Right.
Math, everyone.
Math, can you believe it?
And the spheres and balls specifically are used a lot in set theory, right? Like geometric set theory, like neighborhoods and all that.
Oh, absolutely. It's like you can't go through a topology class without talking about balls.
And what is a neighborhood?
So the most basic definition of a neighborhood is that it's an open set of points around a specific point in your topological space.
An open set is like, if an open set is like a sphere, it means that it has everything but the skin of the sphere, basically.
Exactly.
Versus a closed set, the closure of an open set would be like if you put a skin on it.
Right, and so a closed set, for example, would be just the orange, including its skin.
Yeah. Can a set be both open and closed?
So there are some examples of that. For example, if we're talking about like the real numbers or any like n-dimensional Euclidean space, it's like if you take that whole space itself, it's considered both open and closed.
Witchcraft. Yeah, and if you have a set that is neither open or closed, which would be like if you peeled half the skin off. Basically, the point here is that spheres lend themselves to being used in set theory and topology. All right, so what happens if we define a sphere with other distance metrics? Now, I'm going to just talk about 2 metrics here, the Manhattan distance and the maximal distance, I suppose.
Right, so if you had, say, Manhattan distance, then wouldn't your idea of a sphere pretty much just be a square?
Well, it'd be an octahedron, right, in 3 dimensions?
Right.
And the reason why is because imagine okay, what is the Manhattan distance?
So it's the horizontal distance plus the vertical distance.
And who decides what is horizontal and what is vertical in Manhattan distance?
It's just some x-axis and some y-axis.
Yeah, the mathematician, you have freedom. And so it's called that because in Manhattan, the streets are up and down and left to right. So to go diagonally, you have to go all the way sideways and all the way up. So if something is completely diagonal to you, then it's the least efficient path. But yeah, so you can imagine if you start with the point at the center, right? If you go forward 2 feet and you want a sphere with radius 5, you can only go up and to the right a total of 3 more times. And if you play with this around, you'll see that it is equal to an octahedron, which is basically a square with a point above it and a point below it, and all the points connected together, right?
So Bruce, you just take a square and you cut out all the corners, so you have 8 sides of equal length.
Yeah, exactly. Yeah, you take all the points that are up the top, bottom, left, right, and.
With everything you have on your plate, earning your degree online seems impossible. But at Grand Canyon University, we specialize in helping you fit a master's degree in business into your busy day. Your graduation team, led by your own GCU counselor, provides you with the personal support you need to succeed. Achieve your goals with a plan and team behind you. Find your purpose at Grand Canyon University. Visit gcu.edu.
Forward and back middle points, and you connect them all together. I mean, play around with this on paper and you'll see. But what if we have a distance metric that selects the greater of the 2 or 3 distances versus the Manhattan distance, right? I mean, why is that a distance metric, first of all? Like, why is that valid?
So there's a certain set of rules for determining if something, works as a metric. So a distance metric is pretty much you take any 2 points and there's a certain set of rules that it follows.
And we already talked about Euclidean distance versus, which would be like a plane flying over between two people versus the Manhattan distance, which is if you go left and then up, right?
Right. So there's 3 rules that make a certain metric a distance metric.
Yeah, makes a certain function a distance metric, right?
Right. And so the first one is, so you have 2 points x and y, the distance between x and y, so d of xy, and the distance between y and x, so d of yx, those have to be the same.
Yeah, so for example, so a distance metric can't be, for example, if you're hiking, it can't be how hard it is to travel between 2 latitudes and longitudes, because if you go uphill and downhill, it's a different level of difficulty. So that is not a distance metric versus, yeah.
Yeah, so the other one is the distance between one point and the same point is always going to be 0.
Yeah, if you don't travel, the distance from home to home is 0. Okay, and what's the third one? The triangle inequality, right?
Right. So let's say you have 3 points, x, y, and z.
Let's make this. Let's say we have the first point. Let's say that's Washington D.C., right? The second point is Paris, and the third point is Beijing.
Right. So that's the thing is, so say that we're going from just Washington, D.C. to Beijing. So the distance from Washington, D.C. to Paris plus the distance from Beijing to Paris is going to be at least the distance between Washington, D.C. and Beijing.
Yeah, it's the reason why nobody likes changing buses, right?
Right.
If you change buses, you're always going to take longer than it takes to just go the direct distance.
Exactly, and that's kind of the idea behind the triangle equality, which, if you take graduate mathematics, everything becomes the triangle equality. So be prepared for that.
So let's say we have some origin, which is just some point of reference, right? And we have a metric that is the maximal metric between all the different parameters, x, y, and z. Why could that be considered a metric? Like, and I think you could answer that with the triangle inequality, right? I mean, first of all, the metric is 0, 0. I mean, it's backwards and forwards works, right? But the distance between two things, the distance can't be more than any of the two things. The distance will always be only the maximal thing, right?
Right.
And the sum will always be at least the maximal thing, right?
Yeah, and that satisfies the triangle equality.
Yeah, and so what shape does that result in 3 dimensions? So, for example, let's say we're at the origin, right? If we go up the distance of r, right, we have met the conditions, right?
Okay.
So if we go forward, backwards, left, and right, we're still at the conditions. So it's a cube, right?
Yeah, I can see that.
Yeah. So basically, we have shown that a sphere, using different metrics, can be made into a 6-sided or 8-sided die. So the last thing we're going to talk about is the Harry-Ball theorem. Meryl, what is the Harry-Ball theorem?
So it's like, so you have a 2-sphere. So you have
A 2-sphere being like a basketball filled with air.
Yeah, so your sphere that you're thinking about, your regular sphere in 3D space. So let's say that you have a bunch of vectors, or in this case, hairs, that are tangent to that sphere.
What Meryl is saying is that the direction that the hair grows on the sphere is the most important part of this problem. So please continue.
Right. So every vector is going to be tangent to the sphere, and we call it a 2-vector because it is in the tangent space of a point on a 2-dimensional manifold, which is the sphere.
And any general method of measuring these vectors will require 2 numbers, which is why it's 2-dimensional.
Right.
So what is the Harry-Ball theorem? So we have all these vectors all over. I mean, if anybody's ever seen a map of like hurricanes or something like that, you can imagine it like that on the surface of the Earth. Like wind vectors are a perfect example of this. But continue.
So when we're looking at so let's say that we're talking about a continuous vector field, and this is all 2 vectors on the sphere, then there's always going to be at least 1 point on this sphere. So it's either going to be some sort of cowlick or part or whatever when you're trying to comb the sphere, where at least 1 point is always going to be 0.
Yeah, and I'm not sure if any of you have dogs, but if you notice that all dogs have parts on their fur, or like a cowlick, a lot of times it's on their chest and stuff, and that is a result of the Harry-Ball theorem.
So the way the Harry-Ball theorem works is that if you have a sphere, or something topologically equivalent or homeomorphic, we would say, to a sphere, and you had a vector field on that manifold.
And something homeomorphic might be like a potato, right?
Right.
Would a banana be homeomorphic to a sphere?
Absolutely.
What about a human?
I mean, that depends how many holes you consider a human to have.
7.
But it's like, say that you're just considering the digestive tract, that's a hole in us that at least makes us a torus.
Yeah, so humans are donuts.
Yeah, at
And if you
least.
include nostrils and tear ducts, then we have more.
But yeah, coffee cups are also donuts, but I'm sure you all have heard that at least once. Okay.
So yeah, so going back to the wind example, right? If the wind is kind of like hair being all over the sphere, right?
Right, it's a tangent vector to the sphere.
Yeah, tangent meaning that it is on the sphere. Because I mean, wind does go up and over, but I mean, usually when you see like a weather map, it's left and right, up and down, right? Or like latitude, longitude. So there's always a point on the Earth. This is what this proves. There's at least one point on the Earth where there's no wind at any given time.
Right, because you can think of wind on the planet Earth as a tangent bundle, as in, for every point, there's some tangent vector, and at least one point on this surface, there's a point where that tangent vector is 0, and that means there's 0 wind velocity.
You might be thinking, can any 3D surface become flat? And we have covered this a little bit on other episodes, but it bears repeating that yes, they can. A donut, for example, can be combed flat in pretty much any direction. You can comb it along the side of the donut, right?
Right, and...
So it goes around like a racing loop.
Yeah, because that's the thing, is that with a circle, there's exactly one, curve that we can call a great circle. And it's like, we can go about the torus, the donut, in multiple ways that aren't any one great circle, and have them go in the same direction, the same orientation, and as a result, you don't have to have any one point that's 0 on that vector bundle. It's just, you get to have, a continuous vector field that isn't ever 0.
And so what do you mean by great circle and vector bundle? Let's go through great circle first real quick.
So great circle is pretty much...
It's a line that ends up at where it starts, right?
Exactly, although not every, circle on a sphere is a great circle. It's like the equator is, for instance.
So if I were Forrest Gumping, right? If I were Forrest Gump and Jesus combined and I could run over water, if I ran into a straight line, that would be a great circle, right?
Exactly.
And what does it mean to go straight in a curved space, like the surface of the Earth or the surface of a banana or the universe in 4 dimensions?
Right, so it's the shortest distance between any 2 points on that surface.
And you're saying that donuts don't have a specific great circle, right?
Well, so it's a little more complicated because there's 2 different ways that you can... There's 2 different directions that you can keep going in and get to the same point.
Yeah, you can either go around the edge of the donut, right? Kind of like if you were holding the donut on the side, the place where your hands would curl, or if you were grabbing the donut, trying to place it on top of a coffee cup, for example, so your hands were on the side of the donut. That's a different type of great circle, right?
Right.
And so that's the interesting thing about, I mean, and you could even say that there's a great circle if you angle it, right? So that it curves around into a spiral and gets to its original point, right?
Right, and I think that's part of what means that you can comb a hairy donut, but you can't comb a hairy ball, is that on the hairy ball, you're always going to end up with some 0 point or some sort of part, but on a hairy donut, you try to comb it, and you can just kind of keep going in the same way, either like around the donut or through the center, and it just works because you're not, restricted in that way the way you are on a sphere.
What's interesting is that if you have a one-dimensional sphere, meaning the edge of a traditional circle, you can comb it flat, right?
Right.
Which is the surface of a hyperball, a 4-dimensional ball. A 3-sphere, can you comb that flat?
Evidently you can.
Yeah, and I showed Meryl earlier, but yeah, basically any odd numbered sphere you can comb flat. Any even numbered has cowlicks or parts.
Right. And it's like, for the even one especially, I find it interesting because it's like, take this 3-sphere, which is the, surface of a four-dimensional ball, and that we have proved at this point through the Poincare conjecture that actually is a simply connected three-manifold.
Yeah, the Poincare conjecture it was a millennium problem. The person who proved it turned the money down, which is $1 million offered by the Clay Institute.
Yeah, I would not turn down $1 million.
No, me neither right now. But
in a nutshell, what the Poincare conjecture says is that the three-sphere is simply connected.
And what is simply connected?
So, simply connected is just as a further elaboration upon connectedness of a space. And so,
what does a space being connected mean?
A space being connected means that for any 2 points in that space, you can have an open set that contains both of those points.
Yeah, meaning that you have some kind of collection that has both of those points, right? And that collection has boundaries. The boundary of these points does not exist in the set.
Right, and then there's a stronger condition of connectedness, which is path connectedness, which means that for any 2 points in the space, you can draw a path between those 2 points. And then, so something being simply connected means that, so for any 2 points, you can take any of the paths between those 2 points and continuously morph one of those paths into another.
Yeah, so, I mean, you can imagine this as being like if somebody was washing a coffee mug, right? And then a strand of their hair fell out into the mug, and the mug is kind of wet, so the hair clings to the strand. And if you move that strand around the coffee cup without taking it off the surface, but leave the points the same, this is the sort of operation we mean, right?
Exactly.
Spheres and circles are simple mathematical objects. It is perhaps because of the relentlessness of the curvature, or simply due to the nature of these objects, that we learn quite a bit by analyzing them. We have learned about the nature of the winds on Earth, and how spheres can be things that don't exactly look like spheres. One thing is for certain, however, we will continue to learn about mathematics and our own universe by examining these objects for generations to come. I'm Sophia, and this has been Breaking Math. With me, I had on Meryl Flaherty. Would you like to plug anything this time? How about a song? How about a song that people might like?
Actually, I know what to plug.
All right.
If you are a graduate student at the University of New Mexico, then there is a union forming with the United Electrical Workers. If you happen to be a graduate student worker at the University of New Mexico, then we are forming a union. Go to unmgrads.ueunion.org to find out more about our graduate student union and how we can be recognized by the University of New Mexico as a union and improve our conditions as graduate workers.
And what can anyone who is not a graduate worker, can they do anything to support this cause? Is there anyone to call, letters to write to people?
I would say support graduate worker unions on your own university campus, because they improve conditions for graduate workers all over the country.
Thank you for that. And unions are a very important part of labor organization, and I hope that this message reaches people who need to have this message reach them. And if you have friends, spread the word. I'm Sophia, and this has been Breaking Math. Math, it's beautiful, disgusting, and beautiful.
Disgusting mostly, and I say this as a math grad student.